start and see. Okay, so good morning, everybody. I'm very happy to have Alex Lombardi all the way from Princeton University, telling us about some very exciting works on SNARGs. Yeah,
Hey everyone, thanks a lot for having me. I'm very excited to present this work today. The most recent work that I'll be talking about is joint with Lali Devadas, Sam Hopkins, Yael Kalai, Pravesh Kothari, and Surya Mathialagan. But this is something of a culmination of a sequence of works, two of which I've also included on the slide here, but also including more works than this. My wonderful co-authors and I have been devoting quite a bit of brain power towards trying to solve this problem over the last several years by now. So I'll tell you something about what we've been doing. And I also have a problem for you. I would like you to solve a problem for me that I guess you might call it like a proof complexity problem. You might call it some kind of optimization problem that comes up in the course of this most recent work that might be of interest to this audience. And I'd be very interested if anybody has any thoughts on that problem. So I'll talk about that in the first half of the talk before we get too bogged down in crypto details. Okay. Also, just so I can calibrate, how many of you are like somewhat comfortable with the notion of a SNARG for NP from the beginning? Okay, so maybe like half of the audience. Okay, so regardless, I have the introduction here. So, okay. So just to get us all on the same page, this talk is about constructing a SNARG for NP, which is a really powerful and useful kind of non-interactive proof system. So in a non-interactive proof system, we have two parties, a prover and a verifier, and they're concerned with some claim of the form that some string X, which is known, belongs to some language L. And for the entire talk today, L is going to be an NP language. And in a non-interactive proof system, there is some protocol by which the prover will generate a proof string pi, and the verifier will check this proof and either accept or reject it. And what we're looking for out of this protocol is that if the statement is true, so if X belongs to the language, the verifier should accept some proof with high probability. Meanwhile, if X does not belong to the language, then the verifier should reject any proof that the prover sends with high probability. Of course, as written here, this is what we would call a statistically sound proof system, because right now I'm requiring that no matter what message pi is sent, the verifier is likely to reject. So as written, this is just a fancy way or not fancy, actually, just the standard way of describing the complexity class MA. So by itself, there's no cryptography here yet. So the thing that a succinct non-interactive argument is for solving the following problem. The verifier here might have to work somewhat hard in order to check this proof. So what a SNARG does is it minimizes the amount of work. It's a proof system that kind of looks like this, but where the verifier has to do a very minimal amount of work to actually check the proof. So the way such an argument system works is so far setup looks the same. Just to make things perfectly clear, we're going to think about this proof pi as being generated efficiently by the prover given an NP witness W for the statement. Okay, so completeness is what I said before. And in a succinct non-interactive argument, instead of requiring that there is no proof the verifier would accept on a false statement, we instead just require that it is infeasible to produce an accepting proof. So the relaxation of soundness that we're considering is that, for what we want is that for any efficient prover, as long as the statement is false, the verifier should reject whatever the prover says with high probability.
I think the P star gets W too.
Well, the statement is false, so there's no W. Okay. So this is a relaxation. So that's and we've made the problem easier. The way that we make the problem harder is that we now require the proof is succinct. And here succinct means that the length of the proof should be polynomial only in some security parameter and polylogarithmic in the statement and witness length. Yes?
So for the computational soundness condition, do you let the efficient prover be like a randomized algorithm?
Yes.
Okay, great.
Yes, and we'll also allow it to be just a non-uniform algorithm. So yes, so yeah, so the key efficiency condition on a SNARG that makes the problem tricky is that we would like the proof to be short. On top of that, we would also like the verification to be very efficient. Of course, a verifier needs to read the statement to check the proof. So the way that I'll write verification efficiency here is just polynomial in the security parameter times the length of x. There are various ways that you can reason about the efficiency of a verifier in a SNARG. I'm not going to spend too much time discussing it, but yeah, there are like you can basically you want to think of verification here as being the verifier does some like very minimal processing on the input statement and then also runs in poly lambda time. Yes.
So why in the verification time, the length of x is not inside the point?
Well, yeah, this is this is a stronger requirement, right? I'm saying all the verifier really does. So I mean, this is not what I'm saying, but one way you could interpret this is that all the verifier does is it reads the statement. I could be even. I could make this even stronger, right? It could be like, order length of x plus poly lambda, something like that.
Yeah,
Read the statement and then
I
do some computation on top of the proof, something like this. But yeah, I'm not even going to let you run in input length squared.
Okay.
Yes.
This necessitates lambda to be also the order of polylog x, right? I mean, otherwise it's...
Yes, lambda will have to be at least polylog x.
So that's not very high security, right? Negligible income in lambda.
Sure, but you could all, but I mean, this is parameterized, right? You can set, you can decide how much security that you want. Oh, so I suppose, okay, if you want to implement the SNARG, instead of writing 1 minus negligible and lambda here, we're going to write something like 1 minus 2 to the minus lambda, right? We'll figure out exactly like what you need in order to have a 2 to the minus lambda soundness error, and then you can set lambda however you want. Right, then you can set lambda equals 128 and be happy.
Yeah, but okay. That's for practical methods.
Yes.
But asymptotically, normally I think of lambda as being the length of the input you want.
Yeah, so I guess
Yeah,
on the theory side, you either think of lambda as being polylog length of x, or you think of it as being length of x to the 0.01 or something like that.
So computational soundness is the randomness in respect to, like, is the randomness with respect to the random, the prover or the verifier or both?
I'm sorry, can you repeat the question?
Yeah, in the computational soundness,
Yes.
is the randomness with respect to the prover, the verifier?
Yeah, so the verifier in these protocols is going to be deterministic. So I guess it'll make more sense in a moment, but there's going to be some public parameters that are sampled at random. And so that's where yeah, you can think of the prover as being deterministic actually if you want. So yeah, the probability here is actually over the public parameters that I'm going to write down in one moment.
Oh, just a curiosity, is there any SNARGs of proximity so you can completely get rid of the dependence on X on verifier time?
Yes, in fact, there is a paper in Stock 25 about exactly this question. It's not one of my papers, but it's a cool paper that you can look up. It's literally called Succinct Non-Interactive Arguments of Proximity, and it answers this question in a paper. and yeah, so then this last thing that needs to be said is that because our security model is non-uniform, because we allow the malicious prover to be non-uniform, it's easy to see that it's impossible to have such a proof system under some like minimal complexity theoretic separations as written. So in addition, our protocols, the SNARG protocol has a common reference string that the prover and verifier have access to, and that makes this potentially feasible.
I mean, that's one common solution, but potentially there could be other ways to address.
Sure. I mean, so one is that if you only require uniform security, then there's no clear reason why you couldn't do it without this.
Uniform security, meaning the prover is a uniform.
Yes.
Okay, but is there anything known in that case?
No, there are heuristic constructions. Basically, it's hard to the main heuristic construction that we'll see in a moment can actually be thought of as something that has no public parameters and it looks secure, but it's
For future work.
yeah, it's often pretty hard to say things about whenever you have a type of protocol that requires public parameters with non-uniform security, you can always hope for something without public parameters and uniform security, but it's often quite challenging to say anything about it. Yes.
So how should I think of this common reference string? Is it some advice based on X, or it's just
No, it is independent of X. It is a string sample. It's sampled from a distribution, but it's independent of the statement. And then it's something that you can generate it once. You can think of it as being very public, like posted on a bulletin board. Everyone in the world knows it, and then you can use it to generate as many proofs as you want.
and it's also independent of the language AL?
Well, if you have an NP complete language, you can generate some public parameters, and then if you want to prove anything else, you can first run a reduction to that fixed language and then use this if you want. Yeah, usually we think about just having a fixed NP complete language for such a protocol, and then, yeah.
It is not consistent with your insistence of linear in X because the reduction.
Yes, that is true.
Are you going to consider short common random strings like poly, lambda, log, length X?
Sorry, say that again. Yes. I don't necessarily want to get into this detail too much, but yeah, there are different variants of SNARGs where the reference string is either also succinct or it's not succinct. If it's not succinct, then you have to be careful because what does it mean that the verifier has access to it? So the straightforward way of modeling this is that the prover can have access to a long reference string and the verifier is given the hash of that long reference string. And that's actually the model that we'll be using today. So in fact, the prover will just have access to a long, truly random string, and the verifier will be given the hash of this long, truly random string. Yes.
Heard the notion SNARG before, like of knowledge in the end, like what's the difference?
Yeah, so in a proof of knowledge, what you want is that not just that the prover cannot convince the verifier when the statement is false, but even if the statement is true, that if the prover convinces the verifier, then there is a way of extracting from the prover somehow an NP witness for the statement that it's proving. To somehow say that it actually knows a witness. This is very useful property with the minor inconvenience that it is impossible to build in the model that we're discussing. So there are sort of idealized models where you can hope to build such a thing, but basically, if the proof is short, where are you getting this? Like, if the witness is long and the proof is short, kind of intuitively, where are you getting it from? And in fact, there is a way to formalize this. It's not, in this model, it's not possible to have this property. Okay, so this is our setup. This is the object that we want to build. And the big question, that's been around for a long time by now, is do SNARGs exist? And in particular, for which NP languages do SNARGs exist? And because this is a crypto question, under what computational hardness assumptions can you prove the security of some SNARG? So, as I said, this question has been around for a while. And we've actually had a heuristic construction of SNARGs for NP for over 30 years now, construction due to Killian and Macaulay. In case you haven't seen it before, I'll very briefly describe how this works. So the main tool that you use in this heuristic construction is a Merkle hash tree, which is hopefully something that most of you have seen before, just a way of hashing down a long input into a short output, so that if you want to reveal any small piece of the input, there is a short certificate you can send justifying that the inputs that you started with, let's say that you want to show that the first bit of the inputs that you started with is some value x1, that there's a short certificate of this fact.
Maybe you should say, for those who haven't seen it, that these H's hash pairs.
Yes, right. So in this construction, you start you start with a hash function that shrinks your input length by a factor of 2, and then you apply it in a tree. So every gate that I'm drawing here is an application of a 2-to-1 compressing hash function. And so if you keep hashing in this tree-like fashion, you end up with one short output, and then you can reveal any particular input block that you want, not by sending the entire input x, which would be not succinct, but instead by just sending these siblings of the path of values from.
You send the path plus the
Yes.
siblings, yeah.
Well, yes, the siblings would suffice. But
Right. I mean, the first two, and then you anyway get the
yeah,
guy in the path. And the point is that because of collision resistance, you wouldn't be able to do it unless this was the correct.
yes, because I'm not really going into the proofs involving this thing right now, but the idea is that if you use a hash function where it's hard to find collisions, then you can argue that it's not possible that if you send this path information, that it's not possible to trick somebody into believing that your first bit was different from what you started with.
Why do you call it heuristic?
This isn't the heuristic part. So given this Merkle tree, here's the protocol. So first, let me describe a protocol in which the prover and verifier are allowed to interact. This is not heuristic. This you can just prove secure using any collision resistant hash function. So how does this protocol work? What the prover will do, given an NP witness, is it will generate probabilistically checkable proof string pi, and then it will send this Merkle hash that we just talked about of this PCP string. It will send this to the verifier, which you should think of as like basically fixing the PCP string. It doesn't actually, but that's how you should think about it. The verifier will then sample PCP randomness to check this PCP string. But of course, the verifier doesn't have the PCP string. It only has this hash. So it sends the randomness to the prover. And then the prover reveals the values on exactly the query sets that the verifier needs in order to check the PCP. And then the verifier just checks this. So you have to check. So of course, when I say reveal, I mean you send the bits and you send these paths send this Merkle opening. And the verifier checks that you're not lying about this with these paths. and it checks that the PCP, it also performs the PCP checks. Yes.
This is not succinct. Like the prover runs time in poly X instead of polylog X.
The prover is going to have to do work. Somebody is going to, if you're deciding the language, somebody has to do work. But the verifier will not have to do very much work. All the verifier does is it samples PCP queries, and then it checks. Yeah, then it performs the PCP checks just given the small piece of the PCP string that it actually needs. Yes.
Also, if you use PCP of proximity here, it's already a SNARG or like interactive succinct argument of proximity.
Yes, that's true. Right. So there's no heuristic here. This is perfectly good. And so this will be secure as long as it's hard to find collisions in the hash function. The heuristic step is that if we want a non-interactive argument, we need to somehow allow the prover to generate this entire proof string at once instead of interacting with the verifier. And so this is done using what's called the Fiat-Shamir heuristic, which we're not really going to talk about today. But what happens is you allow the prover to generate also the PCP randomness by hashing its own message.
Sorry, super stupid question. If there's like a random common reference string, can you not like decide beforehand that it's going to be R is going to be the first bits of this random string?
But if you know in advance, if you want to generate a PCP string, but somebody tells you in advance which location they're going to check, then it becomes.
It can send something based on
Yeah.
Okay.
Then it becomes easy.
Right,
Yeah.
right. Thank you.
No. It's an important point. Right. So the way that you can at least heuristically do this non-interactively is using another hash function to generate this R using whatever, all of the available information as input. And then if you model the hash function as a random oracle, you can then argue that that even this non-interactive protocol will be secure. But this is the heuristic. So yeah, if you believe that that this circuit computes a random function, then we're okay. Unfortunately, it has a small circuit, and so it doesn't. But
what do you compute the hash on here?
you can think of it as X along with this first message, this hash.
Oh, so both sides can compute it.
Yes.
Then wouldn't P know it in advance?
But it depends on the on their message.
On the PCP already.
Well, I mean, it depends on this hash value, which depends on the PCP.
The point is that the cheating prover cannot compute a cheating proof pi, and at the same time, H of pi is a place where it will be able to cheat.
That's the religion.
That's the heuristic.
That's the
Religion, okay.
Actually, yeah, our Bloom found the situations where it's
Counterexample, yeah.
Yeah. Okay. Nevertheless, every blockchain company that you've ever heard of is at this point implementing some protocol which does this. So certainly understanding whether or not this is secure is very important. And yeah, as Avi mentioned, there are people like Ron Rothblum that are trying to do good theory research on understanding when this might break and what you can do to prevent this from breaking. But that's not what we're going to be spending the rest of the talk on today. But yes, you can certainly ask about, securely instantiating this Fiat-Shamir heuristic. In fact, this is a question in other contexts that I've spent a lot of time working on in the past. So there's a lot of theory about understanding the Fiat-Shamir heuristic, but this is not what we're going to talk about today. We're going to talk about a different way of building SNARGs for NP. And indeed, it's complicated we still don't have a extremely good definitive answer to this main question that I asked earlier. So very briefly, what are a few things that we know here? So there are some negative results for instantiating exactly this kind of Macaulay type protocol that we were just talking about, which basically says if you're not careful about the choice of either hash function or PCP, if the hash function or the PCP is sort of adversarially selected, then maybe something will go wrong. I want to also mention, at least from a theorist perspective, maybe more like a even more serious concern, which is that there's some sort of black box barrier to building SNARGs for NP. I don't want to get too much into it, but there are some negative results saying that it may be difficult to build SNARGs for NP based on any falsifiable hardness assumption. And when I say falsifiable hardness assumption, I mean something which includes any assumption that a cryptographer is actually comfortable making. So like an assumption as you would probably expect it, of the form that you would expect it to be. An assumption that in some efficient game, that no polynomial time adversary can win the game with probability larger than some number. And so roughly speaking, there is an impossibility result due to Gentry and Wicks, which says that that any language that has SNARG along with nice enough proof of soundness based on a falsifiable assumption is actually not going to be NP complete. It is going to be decidable in time roughly 2 to the proof length. 2 to the length of the proof, which we said was short. And so, if you believe like the exponential time hypothesis, then that will say that the language isn't going to be, that not every NP language is going to have this.
And does this include the CRS? Or?
No. This is true regardless of the CRS length. Even if the CRS is long, this L is just the online proof length. And yeah, so this is bad news because we are looking to build SNARGs for all of NP. Of course, yeah, there are a bunch of details here, and I don't want to get too much into it. But yeah, I guess one thing to bear in mind is that this impossibility result only applies to black box security proofs, which are security proofs that treat the adversarial prover as a black box, that just make calls to the adversarial prover and don't take advantage of its description in any way. Which almost everything in cryptography behaves this way, but there are some notable exceptions that have occurred in the past where you've been able to take advantage of the adversary's description in a security proof. So on the other hand, what we do know how to build already are SNARGs for restricted classes of NP languages, namely that are subject to, the conclusion of the barrier that I just talked about. So languages that are easy enough are often languages that we already knew how to build SNARGs for. Yeah, there are various examples here. Maybe one important one to keep in mind is that if there's no witness, if you're just trying to prove something about a deterministic computation, then it's already well understood how to build SNARGs for deterministic languages. So this we know how to do. There's also a construction of SNARGs for NP making use of this very powerful notion of program obfuscation. There are many things about this SNARG that we're not very happy about. A few of them are that the assumption that you need to make about this program obfuscation is not falsifiable, so it doesn't address this Gentry-Wicks question from before. We also only have a construction, sort of like one very intricate, delicate construction of this kind of program obfuscation based on assumptions that cryptographers are vaguely comfortable with. To say nothing of the fact that any construction using program obfuscation is going to be like embarrassingly inefficient and not something that you could ever actually run. Yes.
Doesn't the program obfuscation allow you to make the barrier result from the previous slide non-black box?
It does not, because the notion of black box from the previous slide is about being black box in the adversary in the security proof. Program obfuscation allows you to be non-black box, like make non-black box use of, for example, a cryptographic primitive, like the description of a cryptographic primitive. But we're not obfuscating the adversary.
Well, you could maybe, but okay, let's continue.
Yes, you could imagine a proof technique where you use yes, certainly. There are simpler things you can do, like the canonical example of how to make non-black box use of an adversary is to run the adversary homomorphically, using a homomorphic encryption scheme. That's something you could hope to do. It says that, yeah, maybe some non-black box technique could be useful, but we've known that for decades, and hasn't been clear how to use it in this case. In fact, we're going to end up making some very strange non-black box use of the adversary in this talk, but in a completely different way from this. If we get there. Okay, so given this setup, let me tell you about some of our results. These are results from all three of the papers that I mentioned on the very first slide. So first of all, and this is a common thread in all of the works, we give an explicit candidate SNARG for NP based on lattices, which are one of the most common popular cryptographic assumptions that people like to work with. This public coin setup comment is just the thing that I said before. That in these constructions, the prover is given a long uniformly random string, and the verifier is given some public hash of that string. And so I would certainly conjecture that this candidate SNARG is sound for all NP languages under the learning with errors assumption, which is the most standard assumption about lattices that you would make. We are not quite able to prove this statement, but I will tell you several things in this direction that we are able to prove. So first of all, under this learning with errors assumption, we can prove that this SNARG is sound for many interesting NP languages, including languages that are hard. So languages that the Gentry-Wicks barrier would suggest to you it would be difficult to build SNARGs for.
NP hard?
No, if it were NP hard, then we would be done.
Okay.
So we're never going to use this in the talk, but if you haven't seen it before, the learning with errors assumption says that if you have a public random matrix A and a secret random vector S, then a noisy version of S times A will actually look pseudo-random. That's the assumption. And an example language, interesting language that we can build a SNARG for in this paper is a language of DDH tuples. So you imagine you have four, the instance is four group elements, and the claim is that they behave this DDH, this Diffie-Hellman relationship, that there are X and Y such that the four group elements are of this form. And it is in general quite hard, it's hard to decide whether, we believe it is hard to decide whether or not four group elements are of this form or not, but we're able to give a SNARG for this kind of fact.
So sorry, so to be clear, the falsifiability is fine here. I mean, it's not, your assumption is falsifiable.
Yes.
But the black box is violated.
So here there's what's going on is something about adaptivity. There's The original Gentry-Wicks barrier is for constructing SNARG satisfying a strong soundness notion where the prover is allowed to choose which statements they are going to lie about. It's called adaptive soundness. So here we're only trying to achieve non-adaptive soundness where the false statement is fixed in advance. Then it seems that even in this setting, there's going to be some Gentry-Wicks style barrier, but the class of languages that it applies to turns out to be different. So that's what's going on here. But then it seems that even then it's not like you're somehow like I guess I'm jumping the gun here, but it turns out that in this setting, like the languages where it becomes challenging to build SNARGs are those not that are in decidable in time 2 to the L deterministically, but that are decidable in time 2 to the L co-non-deterministically. And so since this is an NP intersect co-NP, somehow it becomes okay here. Yeah, so that's somehow what's going on here. That you should think of this first result as saying that that we sort of see how to handle languages in NP intersect co-NP. That's yes.
When you say hard, you don't mean NP hard. You mean just like this hard.
By hard I mean not easy from the old slide. Yeah. Yes.
So when you say like 2 to the L runtime for DDH, this L will be polylog n.
Exactly. So it's hard. We don't expect there to be a 2 to the polylog n time algorithm for deciding.
Do you have like example like hard languages that's the current best algorithm is like 2 to the poly n?
So I don't know. It depends on what you mean by 2 to the poly n, but I mean like for DDH, like it's 2 to the n to the 1/3, right? That's the best running time that we have.
Oh, right. Yeah.
Right. So so what's going on here is that we can somehow handle like NP intersect co-NP type statements, which is much better than we knew how to handle before, but is still probably not going to give us all of NP. So in the second work, we're able to prove the soundness of the SNARG for all NP or for an NP complete language, but not just under the learning with errors assumption. We make additional cryptographic assumptions, and then there are actually a whole bunch of different additional assumptions that you can make. So one assumption that would suffice to prove security of our construction is if you assume the security of the Macaulay SNARG, just a completely different object. You can also assume the security of a certain kind of witness encryption scheme, which I don't want to. I've thrown enough words in this talk already, but under some stronger cryptographic assumptions, you can prove the security of our SNARG.
So you just need to assume any of these things exists. You don't.
That's right.
Don't need to know.
That's right. That's right. You need a bound on the runtime of the algorithms You need to assume that there exists one of these things, and that you where all the algorithms can be computed in some known amount of time, and the construction will depend on that time parameter. Did you have a question? Okay.
You wanted to say that we had a talk about I/O, so somehow that's the thing that we were educated about.
You mean Rahul's talk?
Yes. Yeah.
So somehow what's going on in this second work are a couple of things, but one is that we're somehow proving that this single construction is universal with respect to some class of SNARG constructions. And my personal interpretation of the second work is that the SNARG candidate that we give is in some sense best possible, maybe somewhat akin to this notion of best possible obfuscation. The parallels aren't perfect, but I think they're somewhat similar. So that says somehow, in my opinion, this says that this construction that we're looking at is in some sense the right one to be thinking about.
So should I think about best possible as like, if some SNARG works of this class, then your SNARG
Yes.
will also.
Yes.
But how can that be? I mean, what if someone breaks the lattice-based assumption?
Yes. So you also so it's best possible provided that the lattice assumption is true.
Okay.
You still have to assume like a random walk on the joint random string, like a completely random function.
Well, it's not a function, right? It's just a string.
No, but you say you get a public hash of the prover's randomness that the verifier gets.
Yes, So I assume we have to assume that somehow these two correlated random strings, long random string, comma, hash of long random string, has been generated somehow. We need to trust that this has been generated properly. You could model this in various ways. Maybe this is generated via some joint protocol. Maybe the verifier spent a bunch of work in the past to generate the long random string and computed the hash themselves. That would also be fine. Like there's nothing that nothing is secret, right? Anybody can know any of these, any pieces of these strings. We just need to trust that it has been set up properly somehow. Okay, and finally, in this most recent work, we proved that under the LWE assumption that the SNARG is sound for all of NP, so, like conditioned on some mathematical conjecture or hypothesis about multivariate polynomials, and this is the problem that I want to describe to you and ask for your opinions on, because unlike this, this second result where we're making additional computational hardness assumptions, here I'm just asking. I have a question about a math problem. If the answer is yes, then we're done. If the answer is no, then we can change the math problem and ask again.
So how does this play with the barrier? Suppose you know the mathematical proof of.
So now so there's still this like adaptivity thing that we're proving this, this soundness only for a fixed input. And also the security proof here is non-black box in the adversary. That's a second way. These two reasons that we're getting around the original Gentry-Wicks barrier.
I mean, if I understood correctly, the non-adaptivity just means that the barrier is for.
Yes, although the community is still in the process of understanding this barrier, but
absolutely clear.
Yeah, there are some papers on this. It's a work in progress. But on top of that, this proof is now non-black box in the adversary. Right. So the math problem that we talk about here is something I call the low norm Nullstellensatz hypothesis, and so now I'll tell you about this problem. In fact, in this most recent paper, we even give. So of course we can argue about the original candidate that I've been talking about this whole time, but we also have some simpler candidates with proof of security based on even like number theoretic cryptography instead of lattices. We have additional constructions and security proofs. They're all subject to this kind of math conjecture.
But they're all non-post quantum.
This stuff would be, yes.
Okay.
The lattices would be what we hope are post quantum. Okay, so what's the math problem? So the math problem is related to Hilbert's Nullstellensatz, which probably everybody has heard of, Here we care about a special case of Nullstellensatz that's easier to talk about. So it's Nullstellensatz over the hypercube. So the setup here is that we have a bunch of polynomials in, say, n variables, x1 through xn. And they're multilinear polynomials. We're going to think of them as computing functions on the ±1 Boolean hypercube, right? So that's just like declaring that all the variables square to 1. So I have some collection of polynomials, and these polynomials carve out some vanishing set, right? So we let V be the set of common zeros of these T polynomials. Then what Nullstellensatz says is that if you have any polynomial f, if it vanishes on this entire set V, right? If f of a is 0 for every a and b, then f is in the ideal generated by the original polynomials p1 through pt.
Is it the power of f?
No, it's Boolean.
Over the hypercube, it simplifies to this. Yes, so this is what Nullstellensatz says for us. The question, okay, yeah, and so what does that mean? It means that that you can write f as some combination, as some sum of the original polynomials pi times some coefficient polynomials qi. And the question is, how large do these qi polynomials have to be? Of course, what does large mean? Large can mean many things. So for us, the metric that we care about is the L1 norm of the coefficient vector of these polynomials. So in fact, I mean, there's this Q here is a list of polynomials. So I really mean just take all the coefficients, line them up, take the L1 norm. So just sum of all the absolute values of all the coefficients of all the QIs. That's the metric that I care about.
You don't assume anything about the PIs, they are not low degree or low norm or something.
Right. So in fact, in the end, we care about some one explicit family of P's. You can ask, when is it reasonable to ask the question that I'm about to ask? And I'll talk about, when it makes sense. But yes, so you should think of the P's as actually like individually depending on only a constant number of variables. And that simplifies things a lot.
Could this be like a complexity assumption? Like, is it possible that?
Well, I haven't stated the assumption yet, right?
Well, you're going to say that you can find the, okay.
So of course, how large the Q's are is going to depend on how large the initial polynomial was, right? If I take any f and I multiply it by a big scalar, then the size in this decomposition is also going to be scaled up. This is not a scale invariant problem. So the question is, given how large your polynomial was in the first place, can you get a Nullstellensatz decomposition where the norm blow up in the polynomials is only polynomial in n, where n is the number of variables? All right, so this is the question. And so
Biggest,
polynomial in n.
bigger than.
Yes. Actually, it doesn't have. You can think of t as being n. That's also fine.
You mean for every QI, the L1 norm of QI is most poly n times.
Well, it doesn't matter. There are only polynomially many of them. So for all or the sum, it doesn't matter.
Do you know if B is big or it could be a few points?
Sorry, say that again.
The set V.
Yes, V is going to be big.
Exponential in n.
Yeah, maybe not like 2 to the constant times n, but at least 2 to the square root of n or something like that. Right. So this is the hypothesis. Of course, you get this hypothesis for any collection P1 through PT. You can ask whether or not this is true. And just another way of writing this. This is an optimization problem, right? We're asking about if there's an upper bound on this, this like 2-part optimization. Like take the worst f, provided that it's not too big, and provided that it belongs to the ideal, right? So if you think of A as being a linear function whose like columns span the ideal or something, then then subject to f being in the image of this linear function A, then we're asking about what is the smallest norm of a preimage of f under this linear transformation.
What did you say that the one norm definition was?
Just like, we have a list of polynomials, take all the coefficients, think of it as a giant vector, L1 norm.
So did you give interesting opinions on this conjecture? Okay, we talked about this.
I mean, I've certainly asked a few people, and it's a little tricky to make heads or tails of the conjecture, I would say. Of course, I'm gonna say a few more things about it, but
Is this something you could compute? Given A, you could compute this?
not efficiently. So yeah, so this is the max over a polytope of an LP. So it's not clear. Yeah, I don't know how to compute this even efficiently. Also, it would be efficient in 2 to the n, right? Because the description length of f is actually 2 to the n. But I actually only know of a 2 to the 2 to the n time algorithm for computing this number. Yeah, seems.
And even check it becomes small.
Yeah, so I've done this. Yeah, I'll talk about this. But yeah. But anyway, so we haven't said what the p's are yet, but the way you should think of it is that like there's a pretty like broad class of like nice collections of p's, and if this hypothesis holds for any one of these collections of p's, then our SNARG is sound. Question.
Does the L1 norm matter here? Like you change to other LP norm?
Yes, it does matter. If you change this L1 norm to L2 norm, it becomes extremely easy to prove that it's true, and it also seems completely useless for our purposes. On the other hand, if you replace the one norm by the infinity norm, it's like basically the same. It turns out that this question for one norm and infinity, there's a correspondence between this question for L1 norm and for L infinity. Okay, so let me be even more concrete. Let me give you a very explicit family of polynomials that would suffice, and where I would tentatively conjecture that this hypothesis might be true. So I'm going to rename my variables for a second. Before I was talking about just having n variables. Now I'm going to have n plus n choose 2 variables. I have variables x1 through xn. Then I'm going to have a variable y for every pair of indices I and j. And then the collection of polynomials that I care about, I'm going to have 1 for every pair I and j. And the polynomial is going to be this polynomial that imposes the constraint that yij is equal to the Boolean and of the variables xi and xj. All right, so that's what this math says. So then, if you think about this, so each polynomial is imposing a constraint on a different yij, and so the common vanishing set of all of these polynomials is just this like set of points where the first n variables are arbitrary, and then the last n choose 2 variables are just all the Boolean ands of all the pairs of variables. That's the common vanishing set. And so then the question is, if you have a polynomial that vanishes on this set, can you write it as a small combination of these Pijs?
Can you go one slide back?
Yes.
So why don't you actually also depend on like why can't you move scalars to the PI? Why doesn't this also depend on the norms of the PIs? Or
It does, but I'm not completely free to choose the PIs. In particular, just think of the PIs as always computing a Boolean function, and then their scale is fixed.
Oh,
Okay. He told you the PI.
no, he told us the PIs, right? But sure, he told us the PIs.
Yes, of course. The question is for which collections of P's is the hypothesis useful, and so it turns out it's useful when the PI, in particular, like the setting that we should be thinking about, the relevant setting is when the PIs are computing Boolean functions. That fixes their scale. Right. So now here is a like extremely explicit problem, and yet we don't have a resolution one way or the other whether or not the conjecture holds for this very explicit family. Yes.
F kind of worst case, or is it?
Yes. F is worst case.
It's very concentrated on the coefficients very concentrated.
It's arbitrary. It's for all F.
The F that actually show up. How are they generated?
You're saying when we use this.
For which Fs do you need it?
It's very complicated. You should really think about this as a for all statement. You get a different F for every false NP instance of your NP language.
But the coefficients of F are kind of spread out there. L1 and L2 shouldn't be.
Indeed. So yes, this agrees with my intuition that the F for which it is hard to understand this for are F that are sparse. That I believe. I don't completely have a proof of this, but it seems like the worst F are sparse. So yeah, before talking about that, just for a second, let me say something about what, in general, what's like collections of P's are interesting to me. So roughly speaking, the collections of P's that are useful are, you think of the P's as all being like Boolean functions with constant locality. And the other thing that we need is that a certain computational problem is NP hard. The computational problem is Kalin, where you restrict the assignment to belonging to this zero set V, right? So it's satisfiability of linear equations subject to the constraint that the variables belong to this set V. So I don't really think about V as being some kind of code, right? And then this is saying, is Kalin hard when you restrict your instances to belonging to some code, as opposed to being arbitrary, in which case it's easy.
Or just Kalin, not noisy Kalin.
Right, it's just, Kalin, exact Kalin. So the way that I think of this constraint, I mean, somebody that studies like dichotomy, whatever, will have a better understanding of this than me, but the way I think about this is that the constraint here is that this vanishing set should not be a linear subspace, and it should also not be a union of polynomially many linear subspaces. And aside from that, it's probably fine. So it's a minor restriction on this vanishing set V. And that's so these are the collections of P's that are useful, and we're happy as long as this hypothesis holds for any such collection.
So why just curious, the small union of linear subspace could even be hard for a union, right? Like if you're a low degree function, if V.
Oh, you're right. I think I didn't express this properly. It's not okay. It's not V not being a linear subspace is not sufficient. There are some other V's that are more annoying, but I think I didn't write this properly. But basically, so one way to have V is to have a linear subspace and then additionally impose one quadratic constraint on like on a, a constant number of variables, and the problem is still easy if this is the case.
Sure.
Wait, hold on. No, if V is a union of polynomially many linear subspaces, then you can just solve you can just solve the problem on each subspace separately. Does there exist? Yeah, if it's
No, but
this is global, right? It's the entire inputs belongs to one of polynomially many linear subspaces.
okay.
Then for each one of them, you can just solve a linear system, and then you'll know whether or not the whole thing has a satisfying assignment.
Okay. Yeah. Okay. I was thinking, okay, nah, I'll take it off then.
Yeah, so this is these are the P's that we care about. So what is known about this kind of question in general? So the answer is very little. I was able to find one work by Pravesh and Zhang that studies something kind of like this, although they're in a very different setting. First of all, they're in a setting where the common zero set is empty instead of what we've been talking about. And they're considering the 0-1 Boolean variables instead of +-1, which might sound like a triviality, but is actually not, because it changes the L1 norm by exponential factor. So it's actually a completely different question, as far as I can tell. But in this setting, they are able to show that they're able to prove a lower bound for some explicit family. They show there's some collection of P's that corresponds to the pigeonhole principle, where the common vanishing set is empty, but it's hard to, but there's no like low norm way of writing the constant 1 function as a combination of the P's, which is if you think about it, analogous to the question that we're asking. Yeah, except that there are like several important details that are completely different. Did you have a question?
I'm saying that if T is 1, it's a special case of this. If you're just divisible by a sparse polynomial, then it's known, I think, that F is sparse, right? It's like
yes, I mean if
L1 with sparsity.
Yes. If T is 1, it's also it's because our P's have constant size. Like
even if they didn't, I mean,
yes,
any sparse. If you're divisible by sparse.
I see. Yeah, you're saying even when even if the P isn't sparse, there's still something that you can say. I see.
There's one P and it's sparse, but it's not.
But it's not local.
1. It's a polynomial. Then.
Got it.
L1.
Yeah. So there's this one asymptotic family of counterexample family that we have. But yeah, in the setting that I care about, I have found really nothing in the wild. In particular, I don't know any counterexamples to this kind of conjecture, provided that the P's are sparse and Boolean and 0-1 valued on the hypercube. And so it's easy to prove the hypothesis is true if V is a linear subspace, which corresponds to the P's being monomials, but this is uninteresting, it turns out. It's like both easy to show and also easy to see that this is not helpful for our purposes. And so I can tell you what we know about this very concrete example that I described. So I can tell you that when n equals 3, the worst possible F has very nice structure. That is, among all F, the one with the worst L1 norm blow up in the Nullstellensatz decomposition is just the F which describes the constraint that follows from the initial constraints via the distributive property of of and over XOR, right? So the initial constraints are that Yij are equal to Xi and Xj. And the constraint here is that a product of two Y variables is equal to an and of a product of two X variables and one X variable, which is just just trust me, it's the distributive property. And so in particular, it's easy to sort of write down an asymptotic family of examples that look like this, that follow from the distributive property. And it's easy to see that the asymptotic behavior of this family is like the L1 norm blowup is polynomial for this family of examples. I have to say, showing this was, well, at least I found to be very challenging. This is a maximization problem over a polytope in 64 dimensions, where the objective function is like 180 dimensional LP. The way that we're able to show this is by writing code that cleverly enumerated a set of vertices for the polytope up to some symmetries where the objective function doesn't change under the symmetries, and then brute force calculating the objective on the entire set of vertices. It was it's a non-trivial code that ran for days in order to do this. So
the non-trivial part is to show that F is the worst possible example.
Yes.
And only for 3.
Yes, and only for n equals 3. So for n equals 4, we're not it's too expensive to be able to do that. But I have a guess as to what the worst F is. Maybe don't stare too hard at it for a second. I'll say more in a moment. And for n equals 5, I also have a guess as to what the worst F is. They both have the following structure. They're both just an OR. You should think of this being an OR of two monomials, right? So we have two different monomials in the X and Y variables. They are not local. They're non-local monomials. They have many terms in them. And then the polynomial checks whether one monomial is equal to 1 or another monomial is equal to 1.
Mm-hmm.
So both of the worst examples for n equals 4 and n equals 5 that we've been able to find have this form. I also have pretty strong intuition that polynomials of this form seem to be the worst case.
Can you say why?
Yeah, so this is the smallest sparsity of a polynomial that can be a vertex of this polytope. And empirically, as the polynomials become more dense, the objective function goes down. It really seems that the worst examples are as sparse as possible.
Maybe related to the L2 versus...
Yes, exactly. Yes. So I don't have a proof, but my intuition is that these super sparse examples are going to be the worst. And I do not know how to prove one way or the other that polynomials, even of this very special structure, whether or not they have nice Nullstellensatz decompositions or not. So maybe this is a good special case to think about.
You have Pij for every pair, IJ?
Yes. So we're already well after 12, so I assume that we should stop soon, right?
Okay, how long do you need then?
I mean, that's not the right question. I can go arbitrarily long, but
didn't say anything about the construction.
Yeah, so maybe let me take a few minutes to describe what the construction is. We're not going to be able to talk about how to analyze it, but yeah. So I mean, there's a lot there's a lot to be said here, but let me just. I can really talk an arbitrary amount about this.
I don't have time to run through all your slides.
No, I'm not. I am not.
No, I mean even running.
Yeah. So let me show a picture of what the SNARG looks like.
It's like a Merkel-Tree verification. We can check one slide.
Okay. So here's roughly speaking what the construction looks like. So C is some verification circuit for an NP-hard problem. That unsurprisingly, the NP-hard problem we're going to care about is this K-lin restricted to a code problem that I talked about. So in this case, an NP verification circuit for this problem is just something that takes the witness, checks whether the witness belongs to this set V, and also checks the input-specific linear constraints on V, right? The instance is a collection of linear constraints on V, so you check these constraints. So what the prover sends in this protocol is the following. So the reference string is going to contain a bunch of encryptions of random vectors, encryptions of vectors. The lengths of the vectors are going to be the same as the length of W. And what the prover is going to do is the prover is going to homomorphically compute an inner product of each of these A's with the witness W, right? So the prover is going to compute an encryption of A1 inner product W, an encryption of A2 inner product W, etc. Now we have a bunch of ciphertexts, and the prover is going to hash all of these, hash everything, and also hash an entire description of the computation that it did, right? So if you think about the mapping, think about the first thing that it did, all these homomorphic evaluations. Imagine that it just writes down the transcript for that entire computation, the sequence of steps that it took. It sends a hash of this entire transcript, and then it sends some kind of proof that it sent a hash, that it sent a long hash of a transcript, such that every individual step of the computation, was what the prover is claiming it was. So the proof that it sends is, I sent you a hash of a string that represents the computation of this homomorphic evaluation that I was supposed to do. So the kind of proof that you send here is called a batch proof or a batch argument. It's a special kind of SNARG that's not for an NP complete language, but instead for a language that is about a long AND of a bunch of small NP claims. And it turns out this is a kind of computation that we know how to build SNARGs for. If you want to not prove one big NP statement, but a large number of small NP statements, it turns out there is a way to prove these kinds of things succinctly.
Small being
polylambda.
Polylambda.
Yeah, each NP statement has size polylambda, but the number of NP statements is large.
Yeah.
So this is a kind of thing that we already know how to do. And so we use this kind of proof system here to prove something about this kind of computation. So this paradigm is called encrypt, hash, and batch. In general, you have a homomorphic encryption of something. It doesn't have to be a bunch of vectors. It, in fact, you should think of this as being the description of some circuit. And then what the prover does is the prover homomorphically evaluates this circuit, which it doesn't know, and it sends a proof that while I may not know what this circuit was, I promise to you that I homomorphically evaluated it on my NP witness. That is the general structure of the protocol. And then we've developed a large bag of tricks for arguing about the security of protocols of this form. And yeah, so I guess something about the specific, last result and how it's proved is that the way that we argue security of this construction is that we think about this implicitly defined exponential size constraint satisfaction problem, right? We started with a constraint satisfaction problem, right? But the constraint satisfaction problem that we end up considering is sort of a big extension of the original CSP, where in addition to having all of our old variables, we actually have a variable for every symbol of the Hadamard encoding of the original variables. Okay. So so before we had like n variables, now we have 2 to the n variables. And the constraints in our CSP are just the old constraints along with the BLR test constraints. And so what we end up proving is that if you can break this protocol, then you can produce not a valid assignment to this CSP. If you could do that, then, I mean, the CSP is clearly unsatisfiable if the original CSP was unsatisfiable, so you can't do that. Well, but what we prove is that if you can break the SNARG, then you can produce Shirali-Adams like relaxed solution to this CSP. So some LP relaxation of this CSP has a solution. But on the other hand, we're able to prove that under this low norm Nullstellensatz hypothesis, that the LP relaxation still has value bounded away from 1. So at a very, very high level, this is the way in which we prove the result. Yes.
Oh, why is this non-black box in the adversary?
Great question. So it's okay, maybe it's not, maybe I'll just show it here. So what we prove is that so what I said here, right, this argument about the CSP, it holds provided that there's an adversary which makes the verifier accept in this protocol for all choices of A1 through AR. It has to work for all choices of A1 through AR. Of course, the A1 through AR are encrypted. Nobody can see, like nobody has the keys for this scheme. So nobody actually knows what the A1 through AR are, right? And so if the prover convinces the verifier when the A's are all zeros, then the prover convinces the verifier for all of these, no matter what the A1 through AR are. But the way the security proof works is it really says, like, we derive a contradiction provided the adversary works for all choices of A1 through AR. And so the contrapositive of that is that because this CSP doesn't have this solution, it means that there exists a choice of A1 through AR on which the adversary fails to convince the verifier, which means that there exists a choice of A1 through AR on which the adversary can break security of the encryption scheme. We don't give an algorithm for figuring out what these A1 through AR are, and the A1 through AR can depend on the adversary's description.
So you mean it's non-black box because you are assuming the adversary cannot break the encryption scheme? Is that right?
It's because I don't tell you. It's because it is because although we prove that if the adversary breaks the SNARG, then the adversary breaks the encryption scheme, there is no explicit description of how the adversary breaks the encryption scheme. In fact, the way in which the adversary breaks the encryption scheme requires a piece of advice which can itself depend on the adversary's description.
But that's still like if I have a small non-uniform adversary breaking the SNARG, then we have a small non-uniform adversary breaking the encryption scheme, right?
Absolutely. That's why it's a valid security proof. but it's not a black box security proof because the advice depends on the adversary's description.
I see.
Anyway, this is an extremely subtle point, and I'm happy to talk more about it offline, but probably it's best to stop for now. So what's left to do in the future is, of course, I'd like to see this conjecture resolved one way or the other, and there are generalizations of the conjecture that would still suffice for us. So I'd like to understand this space of like size of L1 norm decompositions of polynomials. It seems pretty unexplored and maybe independently interesting. I also have hopes that the techniques that we didn't get to talk about for these results are also applicable in constructions of program obfuscation. So thanks for listening.
Thank you. So since we've gone a bit over time, Alex told me he's happy to stay after lunch as well. So anyone wants to talk to him, then we can head for lunch.